Welcome to part 2 of a series of presentations I am creating and filming and sharing with you on the evolution of building and how the modern building is contributing to a health crisis. And today we're looking specifically at foundations. The last presentation I did had a bit of a focus on wall assemblies. That was really fascinating, but today we're looking at foundations. Before I started reading about foundations and the history of foundations, I didn't realize how absolutely fascinating it would be. Like, I had no idea that we lost this incredible way of creating foundations when we en masse adopted concrete foundations. There's a really simple design of foundation that absolutely solves so many of the moisture problems that we have today, and we all but forgot it, save a few people, and especially one guy, Frank, in the early 1900s kind of brought it back. So the knowledge is there, but I had no idea that this kind of foundation even existed before I started reading about it. So I hope that you guys enjoy what I have to say today. I was super excited to read about it. So I'm going to start just from the very basics, because that's where I was starting from. So I just want to bring everyone up to speed. What are foundations is the first thing I'm going to ask, and then also why do we need them? So the foundation is basically just the part of the building that connects the building to the ground. Super simple. So what do? The first thing they do is they spread the load, or one of the main things they do is they spread the load of the building. So you've got a roof and wall and furniture and people, all of this stuff that's pretty heavy. And so that foundation is going to spread the weight over enough soil so that house doesn't sink or tilt. The next thing it does is it anchors the building. So it ties the building to the ground so that frost or wind or earthquakes, none of that stuff is going to cause the structure to fall over or to topple, to lose its stability. And then another thing that it does, if it's done well, is it keeps moisture away from the building. Soil is damp and it moves water. That's just a reality of the world. And a good foundation is going to lift that building above that. And if it's done properly, it's going to stop the water from wicking into the structure as well. And finally, it protects against frost. So because there's that water in the soil freezes and it does expand. And if a foundation is not below that frost depth, this freezing soil can cause frost heave. It'll pull upwards unevenly, and it can cause cracking of the walls, sticking of windows, sticking of doors. So for those reasons, we need a solid foundation. So what I didn't realize before starting to properly look into this is that basements are actually just foundation walls. I grew up in Canada, and basements are a fact of life. Everywhere has a basement. But what I didn't know, basements and crawl spaces, they're less common where I grew up and where I've lived in my life, because I've lived in Europe and Canada. So, basements are pretty normal in those places because we've got deep frost depth. So basements and crawl spaces are basically just foundation walls made useful. We were digging deep, excavating, pouring walls, and then why not just use that as living space was the thinking. And I get that thinking. But then what I asked is, why is pretty much like when I started realizing that those musty smells were really what were contributing to making me sick, I was like, but why is pretty much every single basement I go into terrible in terms of air quality? There's always a musty smell. You might even see peeling paint. You might see mold in the corners, dampness along the walls. And the reason is they're below grade and they're right up against soil moisture. So that moisture is always trying to get in, and a lot of the time it does, despite our best efforts to stop it. You add to that modern construction like drywall, carpeting, wood framing, and you end up with mold, because those are materials that love moisture. They hold on to it and they do go moldy. So as I was saying, it's right up against the moisture of the soil, and there's this phenomenon of rising damp, which is just basically the way that moisture travels upwards and inwards through porous structures. So concrete, wood, brick, all of these things will pull moisture inward, and it's done by something that today we call capillarity or capillary action. That's that old phenomenon that they saw already recorded in the Victorian era called rising damp. That happens with even concrete. We didn't know that at first, and it's called today capillarity or capillary action. I can never pronounce it quite right. I don't know. I think Americans might pronounce it different, or because I've only really read it. I haven't really heard it spoken. I don't really know if I'm saying it right. But correct me in the comments. Let me know if I'm saying it wrong. I did want to talk a little bit about the fact that there were cellars in the past, but basements as we know them today didn't exist until we had concrete, or until we really had this idea of, creating structures below grade, and it was really spurred on, or like living spaces below grade, which was really spurred on by concrete foundations. So old houses did sometimes have cellars even before the advent of the Industrial Revolution and concrete. But these were just add-ons. They were small, often made out of stone chambers that were just dug out as sort of an afterthought underneath part of the house. They were for storing potatoes or barrels or wine, and they were not foundations made useful. Dampness was expected, and they weren't finished, and they were not tied into the living system, which is really key. So that musty air stayed put in the cellar. It didn't become part of the air that circulated in the house. However, today, even crawl spaces are normally part of what's called the building envelope. So that just means that those crawl spaces and basements will share air with the rest of the house. So to understand how we got to where we are today and to explore some of the ancestral wisdom that we may have lost along the way, it really helps to take a step back and look at how we created foundations before basements and crawl spaces were even an idea. One of the oldest and simplest foundation ideas is something called the Rubble trench. You basically just dig a trench and fill it with jagged stones. Super simple and genius, which I'm going to get into. So the trench itself is wider than the building wall that sits on top of it, as you can see in that illustration. And what it does is it just spreads the weight of the building over undisturbed soil below. So these are super old. It's a super old type of foundation. They go back as far as Bronze Age Europe, which is 5,000 years ago. The Romans used them under stone and brick walls. The ancient Greeks used them under mud, brick, and timber houses. It was super common in Europe under things like timber frame, wattle, and daub houses. We talked about those kind of walls at length in the last presentation. You can check it out if you're interested in ancestral wall assemblies. It was pretty cool too. So before moving on, I just want to talk a little bit about Roman road and the connection with rubble trenches. So the concept of a rubble trench was used in Roman roads. And I know this isn't to do with buildings, but I thought it was super cool and just illustrates how this concept can be used in different ways. So basically a Roman road was composed in layers. So the very bottom layer, as you can see in the illustration, was just larger stones. Then on top of that, you had smaller jagged stones, which was the rubble layer. And then above that was a layer of compacted gravel, sand, and lime, so like a more dense sort of material, smaller particulate. And above that, you had those large flat paving stones. So the rubble trench layer provided a stable platform, so it spread that weight around of the carts and the armies and all of the things that contribute to the Roman Empire being successful for as long as it was. And also it provided drainage, the spaces between those stones would allow water to drain away from the road, which would protect the road and keep them dry. So that concept was used, as basically a foundation for those famous Roman roads. So thought that was pretty cool and really wanted to share that with you. Hopefully y'all are nerds like me. And Yeah, so I wanted to talk a little bit about the history of rubble trenches in terms of, how we still, like, we owe a debt of gratitude to this guy, basically. It's still kind of in the consciousness because this guy sort of brought them to well, I wouldn't say to the fore, but was talking about them and brought that knowledge into relative modernity. I have to understand that I'm not the first person to be interested in something called vernacular building traditions, which is basically just looking at the history of building, like how in the past ordinary people used local building materials, for centuries. Just kind of looking at that history of building. So this guy was into it as well. This guy, Lloyd Wright, was absolutely inspired when he went to Europe. He saw rural cottages sitting on rubble trenches, and he brought those concepts into North America. He was kind of part of a movement called organic architecture, which is just basically designing buildings in harmony with their site and the environment surrounding them. So I love that concept as well. Let's be in harmony with nature. Let's be in harmony with our bodies as well. So this guy seems like he had some pretty cool ideas that he brought over. By that point in history, sort of in the early 1900s, rubble trenches had been out of fashion for 50 to 100 years. That sort of coincided with the Industrial Revolution, and this was like in the 1800s the Industrial Revolution happened, and this era was really an era obsessed with modern engineering. So they wanted everything to be progress and to be new, and they wanted to kind of shun those older traditions at that point in time. But this guy was breaking the mold. He's like, hey guys, rubble trenches might be exactly what we need. So I'm going to play a little video for you just to give you a better understanding of the way a rubble trench is built. This is a guy building one. I believe this is in Colorado. This is a clip taken from Earth Block International. I don't know why I can never say that. Earth Block International. It's a YouTube channel. I'm going to put the link in the description below. So if you want to go check it out, they have some really cool videos on traditional building, on natural building. So highly recommend it if you want to go check it out. I'll play the video in a minute, but it's just basically they're putting angular washed stone. So again, with those fine particulate removed, they're just putting them into the trench, like into a dugout excavated trench in lifts, which just means that they're put in layers. So they're 3/4 to 1.5 inches big, and those layers are put in, and then it's compacted down, and you'll see them doing that. You don't see it in this video, but you'll often have a geotextile sort of material on either side of the trench, and sometimes along the bottom as well in modern times, and that's just to keep the rubble completely free of fines. So you don't want any sand or silt or anything or other dirt in there. You want to keep it nice and clean so that it maintains the ability to drain water. That drainage ability or drainability is really important to it functioning right. And the other thing I'll mention is you just want it wide enough so the wall that sits on top of it is going to be narrower than the trench itself. Just going to play this here for you. So that gives you an idea of how a rubble trench would be made in modern times. Pretty simple. I'll talk a little bit about the benefits of a rubble trench foundation. So one really big one that I've already alluded to is that it's got excellent drainage. So the rubble, again, angular stones, which creates a very porous path for water to drain. So those big pores allow water to drain. The microscopic pores in concrete, those have surface tension and wick water in, whereas those big pores with this rubble trench foundation is going to allow water to just pour down, to drain out. So the rain and groundwater are just channeled down and away from the building. Today, there's often a perforated drain pipe that's put along the bottom of the trench so that it will take water away, either to daylight or to a sump pump, just kind of pumping it away, taking it away from the foundation. And I think that's a really great modern innovation because we really want to make sure that that water doesn't pool in there. And especially if the soil has got clay in it or something, we really want to make sure that it drains well. And it's a capillary break, so it does not wick water the way that concrete does. It doesn't act like a sponge because it has those big pores, not those little pores. So that rising damp phenomenon doesn't even happen. Super cool. The other thing is it provides frost protection. So the water is going to drain out before it can freeze. So frost without water has no power, goes the saying. It cuts the water supply off that will even cause frost heave. So that's a pretty cool thing if it's done right. Like, we got to make sure it drains, right? But that frost heave issue is eliminated. And also efficiency of the material. It's often cheaper than concrete to buy, the local stone and gravel. And also it's durable. Again, if it's done right, it can last for centuries. And it's not that monolithic concrete mass the way that concrete is. So because that's all one structure, it is prone to cracking. Also, we talked about it's prone to soaking up water because of the tiny pores. But because it's not that big monolithic mass, it can settle a little bit here and there, it can densify a bit, and it can redistribute weight without those brittle failure lines that can happen in concrete. So pretty cool. Like, it's such a simple concept. I was so impressed. I was reading about it. I'm like, what? This is like genius. How did we forget this? Like, anyways, I'm pretty excited about rubble trench foundations, as you can tell, despite the fact that it sounds kind of like gross, like rubble, but it's so cool. We need a better name, guys. So just continuing on a little bit about the limitations. There are some limitations of rubble trench foundations, so I wanted to talk about them. So one is you got to consider the soil and site. It does work best in really well draining soils like gravel and loam. So they rely, if you do want to build with a rubble trench in a clay heavy soil, for example, they're going to rely on very excellent drainage design. Also, they do have structural limits. So they're really great for medium to lightweight buildings. They'll work fine for most houses, but they're not going to work well for under a massive load like a cathedral or a skyscraper. Those need to be engineered, need to be made with engineered concrete, or in the old days, like cathedrals were had foundations that were made from very carefully selected and carefully crafted stone block foundations. So they knew also that kind of foundation wouldn't work under a massive structure. Also, in terms of code acceptance, so most modern building inspectors are going to have no idea about what a rubble trench is or how to sign off on it. So you're probably going to need to find an engineer that's on board with understanding what a rubble trench is and signing off on it. Not impossible, but it is an unfortunate hurdle that is kind of thrown into there. Also, I think I've talked about this already, but I'll just say it again. The drainage has to stay clear. You cannot have fine particulate infiltrating it to clog those voids. It needs to have that loose drainage function. So often in modern times, we'll, as I said, use geotextile fabric liners, as you're going to see in the next illustration here. I'm just going to show you another picture. This is somebody building a modern rubble trench. So you can see the geotextile lining there. That's just going to keep the fines out, the fine particulate, but it's going to let water seep through. So you get that drainage. And at the bottom there, that's going to be a perforated drain pipe there. So that they're using that sort of modern upgrade, that modern innovation, which I think is great. I'm big on modern upgrades, especially to ensure breathability and drainability. We want to keep those things breathing. We want it to, if it gets wet, we want it to dry out, and we want things to drain away. We don't want water to stagnate. So those are some really basic principles of moisture management, and a rubble trench is just so ingenious in its simplicity because it does those things. We can just kind of bolster that ability a little bit with modern innovation. I'm going to talk really briefly about dry stone foundations. It's another type of foundation that is, a historical type. It's not really a kind that I think we should try and bring back just because of some practical considerations, but I'll talk about them a little bit because they were quite a common type of foundation for a lot of history. So thought I'd mention them just to make this presentation complete. So they're basically a dry stone foundation was basically just a low perimeter wall made out of stacked stones, and it was built without mortar between them. So they had to be very carefully selected stones that were placed just so that the building or that the wall would stay. It was also often used without any below grade foundation. It would just simply rest on stable soil or bedrock. And it laid around the perimeter of the structure. So the building walls would rest on top of it. So it would, do things like it would raise the soil, raise the walls above the soil so that it would reduce that contact. It would stop that contact with the damp soil. It would also keep sort of splashback water away from the more vulnerable walls above. Sometimes there was some plaster or lime finish applied to, tighten it up and to make it look nicer. So yeah, as I was saying, the walls would be on top of that. It might be stone or cob or log or wattle and daub type of walls that we talked about, at length. The wattle and daub we talked at length about in the last presentation. And it was found, all over the place from Neolithic Europe to ancient Greece to medieval England. So also very common type of foundation. So I was struggling to find an illustration of what they looked like, but this is like a stone wall, a low stone wall that somebody made in modern times. And I would imagine that it might have looked something like this, the dry stone foundation. I wanted to have a nice illustration for y'all. So I feel like it's starting to get dark. I'm going to try and fix my lighting. I am not exactly a professional filmmaker, but wanted to share stuff with you anyways. It's getting dark out. And I've got my little IKEA lamp over here. So I'll talk a little bit about the benefits and drawbacks. So I kind of alluded to these already. I'll go through them quickly. So keeps the damp away from the walls above, avoids that splashback onto the more vulnerable walls above. Also, it's flexible and breathable, so it could move and adjust slightly, so it wouldn't be prone to cracking the way that concrete is. It's breathable, so moisture would evaporate quite easily. However, a high level of skill is required to find exactly those stones and to fit them in right, and also it's not energy efficient. You can't really insulate it, and it wouldn't fly by today's standards. So just for those reasons, I feel like it's probably not something that we want to bring back, especially considering we've got rubble trench foundations, which I think are quite a lot simpler and quite ingenious. So moving up to modern times, concrete below grade. That was the thing. Let's talk about that. So let's talk first about concrete and its inception. So in 1824, a fellow by the name of Joseph Aspdin, he was a bricklayer in Leeds, England. He patented Portland cement. So he figured out this mixture, figured out adding water, and figured out you could make this monolithic wall, you could make floors, like it was super cool, and he patented it. And by the 1880s and 1900s, concrete footings and basement walls started to appear in the US and Europe, and they really replaced stone and brick in urban housing. So with these early concrete foundations, the builders were really focused on strength, on fireproofing, not on moisture. Portland cement was an absolute miracle. It was cheap, it was strong, it poured in that monolithic way, that big mass, and they assumed it's solid, so it must be waterproof, right? They didn't understand at that point how strongly concrete will wick water through the tiny microscopic pores that are in there. So the result was that, basements were cold, porous, and damp. They smelled musty within a few years, and homeowners just accepted that this is just how basements are. It was only by the mid-20th century, so around the 1950s, that there was an appreciation developing that maybe we should try and keep dampness out of basements, especially considering they're part of our breathing space. So it took people a while to be like, oh, hold on a second, maybe we shouldn't do this. So concrete below grade created the modern basement, and with it there was a whole host of new problems involving dampness and mold and microbial growth. So I'm going to go into, I think you can probably tell that I'm alluding to a lot of problems with basements and crawl spaces as well, just below grade spaces that are part of the living space, bad idea, or part of like the building envelope. So I'll talk about some of the problems. So again, you've got all that concrete, which again is porous, full of those microscopic pores. It'll wick water inward and upward by that capillary action. It's the same way that a paper towel will soak water up. And a basement slab or wall that is in contact with the ground is going to be drawing in moisture. 100% that's going to happen. Also, it's an absolutely immense surface area. So the floor slab is going to cover hundreds of square feet in most homes. Plus you've got all those walls adjacent to soil. That is an enormous surface area that is possibly going to be exposed to moisture if the protective mechanisms that I'm going to talk about in a minute aren't in top-notch order. And that footprint is way bigger than the roof. Even if only a small fraction of that area ends up getting damp, it can be enough to create a moisture and mold problem within the space, which can contaminate the air. And depending how sensitive you are to air quality issues from microbial growth, I'm very sensitive. I know a lot of you that are watching probably are as well. That can cause real health issues. But honestly, I don't think it's good for anyone to be breathing moldy air. And certainly there are certain types of mold that are absolutely, like Stachybotrys is just terrible for everyone. So guys, let's just try and not build in a way that encourages mold and microbial growth. In any case, I digress. So just going on, moving on with the problems. So another issue is that in order to avoid that moisture coming in, like I mentioned that in the 1950s, we started realizing, hey, we should probably do something about that. We started sort of figuring it out, like building science really started kicking in, and we started trying to understand, okay, how does moisture get in? How can we stop moisture getting in? And we didn't want to let go of those below grade living spaces. So we came up with a whole bunch of different ways of trying to protect the living spaces from the moisture. So I'm not going to go into all of those layers right now. I will in a future video. I'm planning on doing a more sort of modern building science video in the future, but just suffice to say, there's a lot of complex detailing that goes into trying to stop moisture from getting in, and it's very prone to failure. So you've got, a bunch of layers of protection, like you've got washed gravel as a capillary break, you'll have a perforated drain as well, you'll have waterproof coatings, you'll have vapor barriers, you'll have sump pumps. So if any of these layers fail, which eventually most of them do, like if a membrane is torn, if a drain clogs, if a joint isn't sealed properly, the system is very prone to leaks. Once moisture does get in, it's often trapped, and with modern finishes such as drywall, insulation, and carpet, it can create the ideal conditions for mold to grow. And then add to that modern structures are really airtight. We're trying for energy efficiency, and understand that's a good aim to have. But that also means that any toxic things that get in, be that soil gases, be that microbial growth, they can't get out. And that really amplifies health risks within the entire house. So I'm going to just talk a little bit about just some of the aspects of modern foundations versus rubble trench foundations. So just kind of looking at how the one deals with an issue and how the other deals with an issue. And I just kind of highlights a little bit more about why I find rubble trenches so fascinating and ingenious. So with modern foundation walls, you have basically footings underneath. So that's just sort of a wider part that helps to spread out the load of the building above over a bigger surface area of soil. So when you have a concrete wall, it's quite rigid and it can put quite a lot of pressure in one spot. And that heavy wall, depending on what kind of soil it is, if it's a softer soil, it'll be prone to sinking or tilting. So we have these footings on the bottom, just a wider bit of concrete that really just spreads the load. So that's the idea. That's how modern foundations deal with that. Now, the ancient method of rubble trench foundation, the rubble trench foundation is actually naturally load distributing, which I thought was really cool. So again, it's built quite a bit wider than the wall above it, and it's not rigid, and it just distributes all of that weight naturally because the rocks themselves can move and shift a little bit. They don't put that very focused rigid pressure in one spot the way that a concrete foundation wall would. So super cool. Also, a little bit more about rubble trench foundations. Just going to mention one thing as well. They often will have sort of a perimeter grade beam, which is, it's normally concrete, but it could be rammed earth. It's that sort of wall that you see just above the rubble trench there. And that will help. It's kind of a solid mass wall, and it will help to distribute the load of the building above to the foundation below. Excuse me. So it helps just kind of evenly distribute that. And another thing I'm going to mention just in terms of moisture management, because it's an important principle, is you can just see in this illustration that backfill. You see where it says grade on the left of the illustration there? That is backfill that is sloping away from the building, away from the foundation wall. Or I guess that's the perimeter grade beam, not the foundation. So you can see it just kind of sloping away, which just encourages that moisture moves away. So you want to not have ground sloping towards a building, you want it to be sloping away. Super simple concept, but you'll be surprised at how often that idea is missed. So I don't want to absolutely romanticize ancestral methods. I really think that we need modern perspectives and combine those modern perspectives with ancient wisdom. We can use our modern understanding of moisture management and understand how ancestral methods really tapped into that knowledge before building science was even a thing. So when we take our modern perspectives and combine them intelligently with ancient wisdom, I think that's the way forward. So rubble trenches really work great when they're done right, when they respect how they work. So we need to approach them with intelligence and understanding. So I do want to say that they are not crawl space walls. We shouldn't try and make them into that. They should not be a part of the building envelope, and their drainage must be protected. I've sort of reiterated that quite a few times, but it's important. And they work best when they're combined with a short wall directly above them to keep the building out of the splash zone and to distribute the weight, as I was saying, into the foundation. And historically, this kind of wall might have been made of cut stone or adobe. Today, we might use concrete. We want to raise that building 6 to 8 inches above the ground. So I did want to talk a little bit about a case study that I found that was published by the Building Science Corporation. I'll put a link to it in the description below as well if you want to go check it out. This was an absolutely scathing look at what they called a rubble wall foundation. And I wanted to talk to you a little bit about how what was done here is not a rubble trench in any way, but also just kind of illustrates that, you know, just because it's like made of rubble and made in sort of an older way does not mean it's going to be healthy. So let's take a look at this and understand what they did and where it went wrong, and understand we're not going to do something like that, right? We know better. So this house that was being renovated that they described in this case study was an 1880 attempt at creating a modern crawl space, like modern back in 1880, and it was an absolute disaster. And they used a rubble wall, which in this wall was just built up of stones, and then there was mortar put between it as well, like to hold those stones in place. It was below grade, it created a crawl space, and it was right up against the moist soil with no attempt to stop water coming in, because back then they didn't even really understand capillarity. This idea of creating a crawl space below grade was really quite a new one that would then be part of the building envelope. You had the full hydrostatic pressure, that water pressure in the soil pressing onto those walls. So of course they would have gotten saturated with all that mortar between the stones. So yeah, this is not what I'm talking about when I talk about a rubble trench foundation. Don't do that. So as you can tell, I'm not a big fan of basements and crawl spaces. They invite contact with damp soil. No matter how well you detail, water is always pressing on the walls. So in my experience and in my opinion, if you try to fight Mother Nature is gonna win. So let's work with Mother Nature is kind of my thinking. Let me know if you think the same in the comments. Love to have a discussion about that. Also, they rely on perfection. You know, they rely on capillary breaks, membranes, sump pumps, all of those things can fail, and they normally do, eventually. And finally, they trap bad air. They are reservoirs of mold, musty odors, VOCs, even radon, soil gases. And in an airtight or relatively airtight house, those contaminants get pulled right into the living space, creating a very sick home. So I want to end on the note of what lessons can we take from this. My aim is really to help you find a way to create a home that's safe and resilient, based on safe and resilient design. So first of all, don't put living spaces in the dirt. Secondly, stop water in its path. So use capillary breaks between the soil and walls. And a rubble trench is a capillary break in and of itself. And keep it simple, solid, and above grade. So historically, people have built on rubble trenches and have put stone walls on top of that before they put the building on top of that. So I see a really good argument to bring rubble trench foundations with a grade beam wall, as we talked about back. But even if you're just using concrete as your foundation, there are other options. You don't have to create a cavity below your living space that then you're going to use as a living, like below, that you're going to like have part of your building envelope, because otherwise it's really hard to deal with like an unconditioned cavity under your building. Don't even go there is what I say. You can use something called a slab on grade foundation or a grade beam on pile type of foundation. There are options, even if you're using concrete, to avoid a basement or crawl space. I won't go into detail about those right now. You can look them up if you want, but those are some basic principles of safe and resilient design when it comes to foundations. And finally, I'm just going to go back to this idea that we should learn from history but not romanticize it. I really think that ancestral wisdom combined with modern understanding is our best recipe for success. So rubble trenches had strengths and weaknesses. We should use the principles that make sense and adapt them intelligently into modern building. So if you're feeling it, like and subscribe, leave a comment. I love talking about this. I love answering questions. I dive deep into these things, and I just adore interacting with everyone about it. So please feel free, ask your questions, leave a comment. Every evening I go into YouTube and I'm like, ooh, has somebody said something? So it makes my life more exciting if y'all leave a comment. And yeah, I'm going to keep creating educational content. I really want to work also on solutions-oriented guidance. I want to help you guys understand building, the history of building, the principles of building, so you can be more empowered to really find ways to create indoor spaces that are healthy for you and your family. See you next time.